You see that?
I have a different. I'm using his file that he sent me earlier.
I was like, whoa, why are you doing that? I was like, okay. Hi, everybody. I'm Jade. Thank you for coming to today's JINA seminar. It's my pleasure to introduce Professor Lawler of the University of Wisconsin. At UW, he is the Arthur and Aurelia Shallow Professor of Physics. He is a fellow of the American Physical Society, the Optical Society of America, and the Institute of Physics. It's quite an honor to have him here because I have gotten very interested in doing the kind of work that Professor Lawler does. And very quickly I realized that when I was reading all these papers, I had a common denominator, and it was stuff that Professor Lawler had already worked on. He's very well regarded in the field. He's actually won 2 awards. For his work in plasma physics, he was awarded the APS WP A-List Prize, and also the Penning Award from the International Union of Pure and Applied Physics. And this year, by the American Astronomical Society, he was awarded the Laboratory Astrophysics Prize for his basic work in atomic spectroscopy, but that's directly relevant for astronomical observations. Over the years, as you can see from this list, Professor Lawler has had a lot of wonderful graduate students and postdocs and collaborators. So let's welcome him today. Thank you.
Well, Johnny, thank you for the kind introduction and presentation. Appreciate it. This first slide has a mistake on it, but fortunately, few people noticed it. Apparently, Hendrik and I have actually published quite a few papers together and forgot. I think we published something like 5 papers together, the Rotor all papers. And I was thinking we had met earlier, but we're on the same papers. That's what happens as collaborations get bigger. Of course, I've had a lot of good graduate students, some of them quite extraordinary, very, very talented collaborators. The Apogee collaboration literally has hundreds of people in it, and I couldn't list them all. But I've listed in bold some of the key people that I'll talk about as we go along through the presentation today. Tom O'Brien, who was one of my students, he is division chief at NIST for both time and frequency and the quantum physics division, which is JOA, so he was one of my best. But I've had many, many talented students over the years. Okay, primordial versus stellar nucleosynthesis. The primordial, this is just kind of a review for everybody. It only produced a few nuclei, hydrogen, deuterium, helium, a little trace of lithium, maybe beryllium, but tiny amounts of lithium and beryllium, mostly those first 3 things. Early stellar nucleosynthesis, it's likely being observed today. The gamma ray bursts break into 2 groups, those longer than 2 seconds and those shorter. And the gamma ray bursts have now been studied for 50 years. It was exactly 50 years ago this year that they were first observed. The long gamma ray bursts are now thought to be early core collapses. And the short ones, with less than 2 second bursts, are thought to be early neutron star mergers. Nothing else seems to fit because 2 seconds times the speed of light gives you a scale for the fireball, and nothing else really seems to fit very well other than the neutron star mergers. So we can build things by nuclear fusion in stars. Hydrogen burning. The sun is burning hydrogen now. It has been for 4.7 billion years, and it'll continue for additional billions of years. about 10 billion years total. Hydrogen burning turns on at 1/10 of the solar mass. Helium burning, the sun's actually going to burn helium. It'll become a red giant. You don't have to worry about this 2 years off. But it will eventually become a red giant, and the surface of the sun will come all the way out to the Earth's orbit billions of years from now. The sun's not heavy enough for the next cycle, which is carbon burning. So the sun, after that red giant phase, will become a white dwarf, and nuclear fusion will stop. Heavier stars can burn carbon. And when you get up to 5 solar masses, the stars can start to burn neon. 10 solar masses, maybe oxygen. The silicon group is the heaviest, about 20 solar masses. And there you produce the iron group, and fusion stops at that point, because fusion changes from exothermic to endothermic at the iron group, and that's it. Now, there's a fabulous range of timescales. Hydrogen burning can last for roughly 10 billion years. Silicon burning at the bottom here, 1 day. So it's sometimes called explosive burning, silicon. So this gets us up to the iron group. How about beyond the iron group? Everything else has to be done, or almost everything else, by neutron capture. The neutrons don't see a Coulomb barrier, and they can fall in and make heavier and heavier nuclei. Now, roughly half of these heavy elements are made by the R process or rapid process, and roughly half by the slow or S process for all of these heavy elements. But those two processes produce almost all of the heavy elements. So, S process, all beta decays can occur between successive neutron captures. And we know where that occurs with absolute certainty because of the observation of the unstable element technetium. Technetium is that funny element in the middle of the periodic table. It has no stable isotopes. The longest lived isotope is 200,000 years. That's very short on stellar timescales. When it was detected in the star, it was made there, and people knew that. The R process, which is the other half of the heavy isotopes, involves a rapid, short-lived neutron blast, and it temporarily overwhelms all the beta decay rates. We're not absolutely certain what the site is for the R process, even after decades of effort. Core collapse type 2 supernova, they were long the favorite site, but it may be neutron star mergers. And we'll talk more about the site problem. And we like to refer to R S process elements in terms of ones whose origin in the solar system was dominated by one or the other process. So, this is the familiar chart of the nucleides. Neutron number on the x-axis and proton number, or Z, on the y-axis. And with the S process, an isotope can walk up the valley of stability. But with the R process, there's a blast of free neutrons, which will push the nuclei out to the neutron drip line. And when we take a little closer look here, there are some isotopes that are only produced by the R process. And you can see why by following this beta decay path through the valley of stability. So these two isotopes are only R process isotopes. So here are some milestones to try to give you the historical perspective. Paul and Merrill, 1952, they saw technetium. This is their star is an asymptotic giant branch star. It's really a red giant. They saw it. Now, these stars contribute S process material to subsequent generations of stars because they have very strong winds. They blow out a lot of material. This is another milestone, Hoyle's 1954 paper. This is a code for Burbage, Lawler, and Hoyle, the Redmond Physics article 57. Very important, influenced a lot of people thinking on nucleosynthesis. And in my own career, I remember I was a faculty member when 1987A happened. This supernova was the first nearby supernova in 400 years since the invention of the telescope. It's good to be lucky. The proton decay experiments were running, and they saw the neutrinos from the core collapse. And it confirmed the basic idea of the core collapse. Not all the details, but that was a real milestone, 1987A, because it told us that the basic picture of the collapse of the nickel iron core was in fact correct. The energy, 99% of it comes out as neutrinos because the mantle of the star prevents a lot of energy coming out as electromagnetic radiation, but neutrinos can slip through. So this was a very, very important set of observations. Well, today the S process can be modeled. The nuclei of interest are either stable or slightly radioactive. They're not ferociously radioactive like a lot of the R process nuclei. And many or most of the needed nuclear data have been measured. So one can model S process abundances and subtract from the total solar system elemental abundance to determine the R process abundance in the solar system. So that is possible today. The R process is still very, very tough to model. Why is that? Well, one of the problems is the nuclei are very far from stability. They're tremendously radioactive. Now, what you're building here, the facility for rare isotope beads, FRIB, here at MSU and for other facilities, similar ones in Europe and Japan, are going to produce the needed nuclear data to model the R process in the years to come. But at this point, the site of the R process or sites are still uncertain in spite of decades of effort. My research, my group's research is on metal-4 stars. They're old stars, and they enable us to trace the nucleosynthesis history during the history of the galaxy. What we need to make this work are big telescopes, UV access with the Hubble, and better Lab Astro. And Lab Astro is what my group works on. Now, why is the site of the R process so hard to determine? Well, neutron star mergers are a viable candidate, and they may be the leading candidate for the R process. But when you do an inventory for the whole Milky Way galaxy, your home galaxy, there really isn't all that much R process material. In ballpark, 1,000 solar masses, maybe a little less, of R process material in the whole galaxy. And if you're only dealing with that much, there's flexibility as to where you made it. If you needed a lot of it, you wouldn't have so much flexibility, but there's not really all that much in the Milky Way. Now, short gamma ray bursts are thought to be from neutron star mergers. Why is that? Nothing else seems to fit. It's 2 seconds, and 2 light seconds is not a very large distance. So astronomers here and around the whole world are keen to record the spectrum of kilonova. Kilonova is what you get from a neutron star merger. A big core collapse supernova is different. A kilonova is not as bright and doesn't last as long, but it's what you get from a neutron star merger. And advanced LIGO may have found one of those. There's lots of rumors right now on the web, but they haven't officially confirmed it. They may have seen one. We're confident they're going to see them. What we need is we need to shrink the patch on the sky. With just LIGO, the patch is hundreds of square degrees and you can't search it. But with LIGO plus Virgo plus maybe one or two more detectors, if you get down to the square degree scale, you'll be able to search it and find the host galaxy of the neutron star merger. And the knowledge, one of the things that we need, and Jadip and I are talking about this, is the knowledge of the spectrum and energy levels of a few times ionized neutron capture elements is really unknown. And so there's lab work that needs to be done. So for a long time, the leading candidate for the site was the core collapse supernovas. And this is the most famous of those. This is the remnant from 1987A. This is a NASA photograph. It was actually not quite in the Milky Way. It was in the Large Magellanic Cloud. And this is a NASA image. And you can see the expanding ring of debris. It was a blue giant. And it was something of a surprise to people who were specialists in stellar evolution. The initial stellar mass was greater than solar masses, and 9 solar masses, and the nickel iron core was above the Chandrasekhar limit. So it was 1.44 solar masses or more, and it collapsed, the neutron star. So can you do the R process in supernova? Maybe. This is from a paper by Woosley and Namka. The proto-neutron star is there at the center. One of the things you need to make the R process work in a core collapse is a lot of three-dimensionality, and that's hard. And another thing you need is you've got to have neutrino physics perfect. And there's some open questions about neutrino physics that haven't been answered yet. And so the neutrino physics may have more surprises in it. And that could change the picture quite a bit. Going back to the late 1990s, there was a group in Germany, and I think they really got it going. Thieleman's group, they started thinking about neutron star mergers as a site for the R process. So the neutron star mergers, when the neutron stars touch, the tidal forces rip the neutron stars apart. And it's a little hard to see. Now, some of the ejected material falls into the accretion disk, but the shaded stuff is supposed to represent material that gets away, okay, that goes out into the ISM. The modeling has gotten a lot more sophisticated. This is from a recent paper by Rodrigo Hernandez, and what he's plotting here, he's showing the light curve. This is time in days. This is in the ultraviolet, in the visible, and this is in red. And this complicated plot here gives the speed as a fraction of the speed of light of the ejected material, and y sub e, the electron fraction, which turns out to be important, producing a neutron-rich environment. So the modeling has gotten a lot more sophisticated, but we still don't know the answers. We need real measurements. So you might ask, well, where are the neutron star, neutron star, neutron star plus black hole mergers from LIGO? There's a simple explanation. A couple of years ago, we had a speaker from LIGO, and he said, well, they're going to see the big black hole mergers first, and the reason is they'd achieve full sensitivity at 100 hertz. And you can use undergraduate physics and some knowledge about neutron star radii, and you can work it through, and the chirp from a neutron star merger is up around kilohertz. So they haven't seen them yet, but they're going to see them. So that's it. It turns out that the radius of a neutron star and the radius of a black hole of the same mass really aren't all that different. They're pretty close. So that's why they're not seeing the neutron star mergers yet. They're going to see them. And soon. How soon? Well, they may have already seen one. There's rumors all over the place that they saw one. But I think they're going to see them within the next year or two. So all of you will be part of this excitement. The neutron star mergers are definitely coming. So how does spectroscopy fit into this problem? That's what my group does, is spectroscopy. Well, I like to teach spectroscopy, and I always like to point out that 100 years ago, spectroscopy played a central role in the development of quantum mechanics and modern physics. Spectroscopy was really critical in that. But 100 years from now, it's still going to be spectroscopy that tells us about the remote universe outside our solar system. The nearest stars outside of our solar system are Alpha and Proxima Centauri, and they're 4 light years out. We're not going there. 4 light years is a long way. Chemical rockets have gotten us up to about 1/100 of the speed of light. You can do the arithmetic, it would take centuries to get to the nearest stars. Now, science fiction writers always like to solve this by inventing a warp drive. We're pretty sure that's not going to work because it violates special relativity and it interferes with our ideas about causality. And you don't have physics if you don't have causality. So we're pretty sure a warp drive isn't going to work. It's a shame. I tell people this lately where they always feel surprised and sad look on their face because they grew up watching Star Trek. Okay, so how do we do spectroscopy? Well, we mostly use what are called Fraunhofer lines. And Fraunhofer, who gave its name to these lines, this is the solar spectrum, wasn't the first. It was actually Wolfstein, who saw these features in the sun spectrum. But Fraunhofer really did the following, and he launched a careful study of these features. And he measured them using prisms, that's all they had, and he named the features A through K. And, well, that's probably the ones he gave lowercase letters to. We have since matched them all with atoms and ions, of course. Fraunhofer lines in the sun and stars are really just from the temperature gradient. When you look at the sun on a clear day, you see this half-a-degree sized disk. It looks a lot like a black body at that temperature. So it's about 5,800 Kelvin. As you go below the surface of the sun, the atmosphere gets hotter and hotter as you go toward the core of the sun. So the way the Fraunhofer lines are formed is that the inner, there's a sharp boundary here. The sun doesn't have sharp boundaries, obviously. But the inner surface provides a continuum, and you do absorption spectroscopy on the atmosphere of the sun. And so this is modeled using equations for radiation transport. There are no sharp boundaries, obviously. The most popular classic models use the LTE, local thermodynamic equilibrium, and one-dimensional approximation. You can do more sophisticated things today. But that's the basic idea. You use the hotter inner parts of the sun to provide your continuum for absorption work on the outer star. So the gamma ray bursts were discovered in '67, and they've been studied in great detail with Compton Gamma Ray Observatory, VATSI, a whole series of missions up to Fermi. Now we can see the same products from those early nucleosynthesis events in metal core stars. And we needed Better Lab Astro, a successor to the Hubble, and large ground-based telescopes. So this shows you the difference. What does the sun look like in the near ultraviolet? Well, the line density is so high, you can barely tell where the continuum is. Here are 2 metal core stars, and we see these neutron capture elements popping right up with very clean absorption features in HT 122-563 and CS 22892-052. Those are sort of like the dresses for the stars in the sky. With the metal core stars, we can see the heavy elements, and we could see them cleanly. What this is telling you is that most of this absorption in the near ultraviolet, most of these line features are in fact iron group elements. So in 1980, what was left to do? Well, the wavelengths had been measured pretty well, but we needed these transition probabilities, these Einstein A coefficients, because you've got to have those right if you want to do quantitative spectroscopy. And the problem was there wasn't any really good, fast, accurate, and very broadly applicable measurement technique until we had tunable lasers. Well, when did we get tunable lasers? Organic dye lasers were the first, and they were invented in 1966. Two different groups, Peter Sorokin in the US led one group, and Schaefer in Germany led the other. The dye lasers are the chemical dyes that color your clothes and food. You can make them laze under the right circumstances, and they give you very broad tunability. So that's the importance of them. So pulse dye lasers by the mid-70s, we had optical bandwidths that were comparable to Doppler widths. We had pulse durations of a few nanoseconds. It turns out the duration is not as important as the cavity Q, and this is kind of a subtle question. What you want when you're doing time resolved measurements is you want the pulse to turn off very abruptly. You don't really care exactly how long it is, but you want it to turn off. And if you have an ultra low Q cavity, it does that for you. We had the right rep rates, and we had the tunability. With dyes, without much effort and a few crystals, you can go from 200 to 800. We've actually tuned our system below 200 down to 150 or so. But that requires a little more powerful laser. So what we did that made a difference is we developed a simple way to make atom-ion beams. And the first two students listed on that first slide, David Cat and Susan Solly, they were listed in bold. They helped me develop these beam sources. And our source worked well with all metallic and most non-metallic elements. It was highly reliable, downtime less than 1%. We measured the absolute flux by growing the film and weighing it. So we knew what the absolute flux is. The beam is rich in metastable atoms and ions. So we can do many EV above the ground level and use that as a lower level for laser-induced fluorescence. And we could measure radiative lifetimes that were accurate to a few percent. We could do it fast. We could do many per day. So that's what our source enabled us to do. So the idea is very simple. All the absolute information is in this total decay rate, the inverse lifetime. And that's the summation of all these Einstein A coefficients. If you have that lifetime and you're sure you have it, then all you need are the branching fractions, a relative measurement on these different lines. You're no longer constrained to look for a plasma in local thermodynamic equilibrium. You can work with any plasma you want and just get the relative strength. Plasma has to be up. Yeah. So here's our source. It was just a hollow cathode discharge of a hole in the bottom, and it would produce a jet of atoms and ions. A lot of groups were doing alkalis, sodium, lithium. Okay, we could do iron, cobalt, nickel, tungsten as easily as they did the alkalis. And we would use a little short pulse laser and selectively excite atoms or ions in this jet. And then we had a fast data collection system and a transient digitizer to record the decay curve. So here's a decay curve. This is samarium number 2525. Yes, we took thousands. All of these notes here help us to set up the exact same experiment. The time window is 50 nanoseconds. This is the first part of the decay. And there's a little dashed line there. You have to look very close. You can see it more clearly here. This is the second part of the decay. These lifetimes are single exponential fits. 12.7 nanoseconds, 13.1. we know the lifetime of this upper level to within a few percent. Here is a longer lifetime, about 100 nanoseconds, 105, 104. That's a cable reflection. It subtracts out. Okay? So that's a cable reflection, but you'll see that it subtracts out. This is background when you tune off of the transition, and this is the foreground when you tune the dye laser onto it. That's a cable reflection. It subtracts out. Single exponential fit, 105 nanoseconds, 104 nanoseconds. You know the lifetime very well. We didn't just assume that we had all the systematics right. We checked everything we could think of to check. We varied the beam intensity. We were worried about collisional quenching. We could throttle the pump down. Zeeman quantum beats. The laser's polarized, so it could process. So we zeroed the field to within 10 mellingauss for short lifetimes, but for longer lifetimes, we couldn't zero it accurately enough, so we turned it up and just made the spin rapidly, process rapidly. And our ultimate end-to-end test was the periodic remeasurement of benchmark lifetimes. Lifetime where the theory was so good that people thought it was good to a lot better than 1%. And they do exist in helium and beryllium and a few other elements. So this is a comparison of independent sets of LIF, laser fluorescence lifetime measurement, from University of Western Ontario versus our measurements. This is a 1 standard deviation Gaussian, and this is the histogram as a function of combined uncertainty. This shows that, if anything, we've overestimated our uncertainties on the lifetime measurements. So the LIF measurements provide the absolute scale. Ab initio theory can provide us with the branching fractions, the branching ratios, and simple spectrum. But we want to work in more complex spectra. Theory can't do it, so you have to measure them. Okay, the way you want to measure them is using a Fourier transform spectrometer. James Ball, deceased now, unfortunately, built a great one at Kitt Peak, and we used that for years. There are additional FTS instruments at NIST in Gaithersburg, in this country, at Lund in Sweden, and at Imperial College London. Very high spectral resolving power, excellent wave number accuracy, extremely broad spectral coverage, very high data collection rates, and they're insensitive to source intensity drifts, and they have a very large acceptance, a very large aton do. Another collaborator who was highlighted, Ford Whaling at Caltech, came up with a way to produce a relative radiometric calibration of FTS data. So both of these people were collaborators who really boosted our program tremendously. So what do the branching fractions look like when we compare to University of Western Ontario? Again, this is in Samaria, Samaria. Well, I'd like to have that histogram entirely in here. We may be slightly too optimistic about our branching fraction uncertainties, or UWO maybe, or maybe we both are. But we're close on the branching fraction uncertainty. This is a comparison to some measurements from Oxford. Nobody's ever been able to really test them. But they claim that their relative GS were good to 1%. They were absorption measurements. NIST says they're probably good to that. Anyway, we've compared to them on a couple of occasions. That's an outlier, that one line there. That's an outlier. That was a misidentified line. But the stuff from Oxford, this would be Blackwell and all, is thought to be very, very good. So what Chris Sneeden always liked, he's another extremely important collaborator, is this is the solar abundance of Samaria. He switched to our oscillator strengths and things collapsed. The scatter just collapsed. And he really liked that a lot, because that gave him great confidence in our transition probabilities, our oscillator strengths. So this is as a function of wavelength. Each one of these is a different line in the sun, and various sources from different earlier efforts on samarium, and this is new data from our paper. with much smaller scatter. So pristine mode is like that. This is from the Sneed et al. Papers. It actually involved more than a decade of effort by my group. What it is the R process abundance pattern from 5 metal core stars. And it's very consistent across space and time. The lines here represent the solar system R process abundance. So if you remember to what I said earlier, I said you can model the S process and subtract it away from the total elemental abundance pattern and get a solar system R process abundance pattern. So this is what we did here. And what this tells us is that the R process, whatever it is very, very consistent across space and time. So, the rise of the S process. Jennifer Simmer was one of Christine's PhD students at Texas. This axis is iron to hydrogen, it's metallicity. So, and it's logarithmic and it's normalized to the sun. So 0 is solar metallicity. There the iron is down by, switch pens here. The iron is down by a factor of 10, by a factor of 100, by a factor of 1,000. So this axis is look-back time, is what it is. Metallicity, although the exact connection between look-back time and metallicity is not well understood, it's more or less what it is. And this is the ratio of lanthanum to europium on a logarithmic scale. Each data point is a different star in this plot. And what this plot is telling you is that the R process turned on very quickly, whatever it is, turned on very quickly when the galaxy and the universe were quite young. That's what you get from this plot. Okay. R process peaks. Well, there are peaks in the R process at these neutron numbers. And in some sense, they're the foundation of the R process distribution. The first peak is around arsenic and selenium, and then around the second peak around tellurium, and the third peak is around iridium. The third peak had been observed, but not the first 2 peaks. Well, Ian Roederer and Hendricks on these papers. All of you like to remember it this morning. Ian Roederer got these spectra of tellurium. And he had multiple lines, and this was the first observation of tellurium on metal core stars. Initially, he only had a single line detection, but he got it in multiple stars, and it's right. He got it right. Well, after that, Ian and I were talking, and we said, let's try to do the rest of it. Let's try to get all 3 R process peaks. And so we started combing through the Hubble archives, and we were able to pick up arsenic and selenium, but only for a single star, which is a shame. You'd like to have this for multiple stars, but it was only for this one star, HD 16617. But we got the complete, all 3 peaks for that one star, and those fell right on the solar system R process abundance curve. So that came out a few years ago in 2012. I wish we could get that complete pattern for additional stars, but we need to get a lot of Hubble time. Okay, the STS does more than just the branching fractions. You can get hyperfine constants, and you can get isotope shifts when you need them. So I'll give you a couple examples of that. This is ionized holmium. It's a near UV line. This is a classic flag pattern, as we call it. And it's a hyperfine pattern, and we can get respectively accurate hyperfine constants from a pattern like this. You can do better with a single frequency laser, and better yet with RF techniques. But we can do well enough with FTS data in many cases. It does matter. This shows two lanthanum lines in the sun. If you didn't know about the hyperfine pattern, you would suspect that this line was blended and this was not. Lanthanum only has one isotope, but it has this widely varying hyperfine structure. So every other element tends to have an unpaired proton and can give you hyperfine structure. Okay, in recent years, I'm going to stop in a minute. I have to skip some things. We started working on the iron group elements because there were open questions about the production of the iron groups. As you go from solar metallicity to -7, that's 1/10 millionth the amount of iron. And part of the question was the photospheric models, where the LTE one-dimensional approximations breaking down. So this is the paper that really launched it. This is as a function of metallicity and look back, and this is manganese to iron. Now, here's cobalt to iron and chromium to iron. When you compare cobalt to chromium, they separate by a factor of 10. That's a big separation. That's a very big separation. What's causing that? Is that teaching us something about the early core collapse supernova, or is it teaching us about the limits of a 1D LTE photospheric models? Well, the early core collapses were different. I mean, the masses, I thought, were much higher rotation rates, zero or near zero metallicity. The photospheric models are also an open question. Now, 1D LTE models work great in a metal-rich dwarf star like the sun, because the electron pressure is mostly from the metals, the free electrons. And the densities are high. But when you go to metal core stars, you lose that electron pressure. And when you go to a giant star, a metal core giant, and that's what observers always want to do because they're starved for photons. They're trying to do very high resolution, high signal and noise measurements. So they want to go to giant stars. Well, then you drop these densities a couple more orders of magnitude and you worry a lot about LTE. So whether or not it's really in thermodynamic equilibrium. Well, we started down this with manganese, with some work on ionized manganese. Betsy Den Hartog, who was involved as a former student who continues to work with me as a staff scientist. We were squeezing the error bar down to 100th of a dex, that's 2.3%. It's a lot of work to squeeze it down, and you've got to have a favorable spectrum. But the initial application revealed non-LTE effects that were way, way bigger than that, and we didn't really have to squeeze the error bars that time. What we need are more, what we call them, highly reliable lines. What's a highly reliable line? Well, it's a UV line to the ground or low metastable ion guns. So you've got to have bubble time. When you do a little bit of StatMech, well, you see that the iron group elements are all singly ionized. It's a very good approximation, as are the heavier elements. But you see something else. Almost all of the photospheric material is in a few levels when you do the StatMech. But the Boltzmann factors, it's all in the ground level and the first few metastable levels. When you use lines that connect to those levels, you don't worry about these reservoir levels getting out of LTE because they have a whole population. It's not possible for multiply ionized iron group species to persist in neutral hydrogen atmosphere. They'll charge exchange right away. So the primary reservoir levels are the ground and low metastable levels of the ion. They have most of the photospheric content. So those are the levels which are guaranteed to give you the right So we're focusing a lot more on those now because we want to really put some limits on it. I'm watching the clock here, and I may skip through a few slides. We got to build a new spectrometer. The non-LTE effects are there. Skip through a few more. If you want to look at these, they're online. Okay. There's lots left to be done. The spectra of multiply ionized neutron capture elements needs work. And Jadid and I are talking about that. Neutral europium, that's my favorite art process element, if you're wondering. We know 592 levels from experiment. Singly ionized europium, we know 163. Those are both pretty decent numbers. Doubly ionized europium, the third spectrum europium, we know 118. Triply ionized, we know 13. Quadruply ionized, we know 2 levels. Well, actually, when you look, you see that one of the levels in this gives you is the ionization, and the other is the ground state. The ground state is 0 by definition. So really, you just know 1. And you see the same thing in gadolinium. You just know, by the time you get to 4 times ionized gadolinium, you just know 1 level. And you've got to have knowledge of at least a few more levels to deal with these neutron star mergers. So finding the energy levels is the first step toward more quantitative spectroscopy. Now, what's changed? Well, we have new technologies. This is classical spectroscopy. We have laser-driven plasmas, LIBS, laser-induced breakdown spectroscopy. There are tokamaks, electron beam ion trap machines. So there's lots of new pieces of technology that we can bring to bear on this problem. And it is important. It is important for understanding the light curve from neutron star mergers. So advanced LIGO, they're going to see these neutron star mergers when they get full sensitivity up around kilohertz. We don't have good statistics on the neutron star mergers because we don't really know the opening angle of the gamma ray beam. If you try to explain these gamma ray bursts using isotropic sources, energy budget really gets out of hand. So you need these things to be beamed, and we don't know the beam angle. So Virgo's already online, and they're rapidly shrinking the patch of sky. So the kilonova from the merger, neutron star merger, will expand and cool. It's going to be brightest, most easily observed at the beginning, obviously, because it's going to expand and cool, and the emission will shift in the infrared. And so we really need to understand the line spectra of multiply ionized heavy elements to model the early kilonova. And that's what Jadid and I are discussing today. So I think it's about time for me to stop, and I'll try to answer a few questions because this is supposed to be more of a give and take. So I'll stop here, and I thank you for your attention.
Plenty of time for questions.
Yes.
So in one of the data you showed that you analyzed all data with Ian Lawler, could you go back to
Yes.
the balance that went quickly, but
I know I went quickly through that. It's right about here.
yeah, this one.
Yes.
So I was just curious what's going on between mass or atomic number 40 and 50, where the data doesn't look like it's following R or S, or if you know.
These points here.
Yeah.
I don't have an explanation for those points, but thank you for asking the question. I can't explain those through there. Something else is going on there that I really can't quite understand.
Well, that could be some net contribution.
Well, that may indicate that there's multiple things contributing. there was a very recent discovery of a whole bunch of metal core R process-rich stars confined to one dwarf galaxy called JINA-CEE. And obviously people are racing to do more spectroscopy on those stars because whatever happened there probably was a common event. It's a pretty small dwarf galaxy. So there's that one discovery by Keith Bechtel and collaborators doubled the number of known metal core R process-rich stars. That one single discovery of particular two. So there's a lot of speculation in that. Some people are arguing that it's definitive evidence for neutron star mergers, but I don't want to try that.
If there's multiple sources for the R process and they're sort of rare events, like you have supernova in some cases, neutron star mergers in other cases, how smooth do you expect the galaxy to be, uniform do you expect the galaxy to be in R process?
It'll be pretty clumpy early. So that's one of the sort of loose ends. But it may be, we were talking about this today, it may be that the supernovae are doing the LIDAR process for materials and that the neutron star mergers are doing the heavier ones. There is no evidence that really rules out that sort of a scenario. But I think it's hard to do it all just with neutron star mergers because it's hard to make enough neutron star binaries with small separation. You've got to do it right at the beginning. People they come up with scenarios, but they're too contrived, they're too fine-tuned. I don't think they're going to work. That's my own opinion. Right.
We're talking about iron and chromium and metal core stars.
Yes.
And how the ratios differ. And sorry, I missed it. Did you find anything that helps resolve that?
Yes.
So do you understand now?
Well, I'm going to give you my opinion. Christine might not agree with this. I think that this plot is mostly due to the limits of the photospheric model. And I have good reasons for saying that. I think there are some effects that were due to the nuclear physics being different in the early core collapses. But I think this is mostly due to the breakdown of the one-dimensional LTE model. And I have reasons for that. We do see non-LTE effects. I didn't go over all those slides, but for instance, the ground level of neutron chromium and neutral manganese drop way out of equilibrium. And we know those oscillator strengths to like a couple %. And the branching fractions are unity, so none of the radiometry, which is hard, comes in. Branching fractions are unity. So we see these departures from LTE, and I think this is mostly due to breakdowns of the model. Christine might not be. I'll give you my opinion based on looking over all the data and thinking about it.
They have to follow up then. So are you missing, are there more measurements you want to do, or is it a modeling?
Well, what we need is to take all the new iron data, and we have a lot of it. We've done nearly all the, I'll just show you a few of these since we have time. Once we got the biggest shell working and aberration corrected in the UV, we could work on these really weak lines. And we played a little trick to overcome astigmatism. This is for instrumentation specialists. Okay, we worked on neutral and ionized titanium, on ionized nickel. We worked on vanadium, neutral and ionized cobalt, neutral. And more recently, we've done chromium. That's out now. And so we've done a lot of these. What needs to be done now is, and this is in progress, you have to go back and look at the metal core giant. all the tests we've been doing so far, we're with this favorite star. It's a metal core dwarf. What did I do? I did something bad. Well, this is a good time to stop. There was a template star that we were using, and we didn't see many departures from equilibrium other than this neutral, the neutral resonance lines. But you have to go back and do the same tests in the metal core giant, where the densities are a lot lower, and see whether or not the departures from equilibrium grow. And that's in progress. People are doing that right now. We've got a lot of the lab spectroscopy pretty well in hand. There's always more to do, especially on iron. You can work on iron forever. And iron is so important in astrophysics. You can work on it forever. I don't know what I did. I pushed the wrong button. Well, anyway, what happens when you go from a dwarf metal core? These abundances from the neutral line drop further down using the same atomic data as you go to the metal core giant. And that really kind of is a clue that it really is a departure from LTE. But we already know those oscillator strings well enough. Resonance line oscillator strings. Yeah, 2% maybe. So they're not doing this. This is a logarithmic scale. So a tenth of the dex is 23%. In astrophysics, people like the logarithmic scales. So I did something with this. Any other questions?
Yes. Quick follow-up on that. Is chromium and manganese, are these special cases, or do you expect similar problems for other elements that when you go to low velocity, the data become unreliable?
Well, there's another problem that we're still trying. I'll show you this problem in manganese. This is very clear. That is a metal core dwarf. And if you watch what's happening right here, so this is all reference to the ground state of neutral manganese. You watch those lines right there. When you go to a metal core giant, they drop further down. This is a giant metal core star. And that's a non-LTE effect. And those oscillator strings are really well known. Now there's another effect, it's wavelength dependent. We call it the Lawler dip. It's about 2/10 of the dex. And it's right where the Lawler series ties on to the photoionization continuum. And that's a little tricky for several reasons in modeling the atmosphere. And it's also where you bridge between calibration sources when you're using a tungsten lamp in the optical for your brightness calibration and you switch to the deuterium and the UV. So it's a problematic region. The Lawler dip shows up with a couple of lines that have branching fractions that are very high near unity. I think it's an LTE effect. Not everybody's going to agree with me on a non-LTE effect. Not everybody's going to agree with me on that. So I have reasons for thinking it's a non-LTE effect, but my collaborators might beg to differ on that. It's a lively collaboration.
But what about other elements like europium or
okay,
are these also unreliable?
No. With the rare earths, remember the abundances are a lot lower to start out with. And so virtually all the measurements we made were made using what we would call highly reliable lines. So those are going to, all those rare earth measurements are rock solid. They're fine. All the rare earth measurements, because we were using UV lines or optical lines that went right to the ground and low metastable levels of the ion. Those are the reservoir levels. No possibility of those changing. So those are solid. It's the iron group. When you're working over a factor of 10 million in iron density, where you end up using neutral and ion lines and lots of different lines, that's where you get into these non-LTE issues, but not with the rare earths. I hope I answered that. Okay, I kept you here late already, so I really thank you.
Yeah, thank you, speaker.